Hi, everyone. So we are talking about AP Stats Unit 2, exploring relationships between two variables. So we are going to get started with this. I went ahead and filled in a bunch of the notes for you just so we can make these notes go quickly because, who wants to write all that stuff? So you've done a lot of this stuff before. We're going to talk about scatter plot. So what is a scatter plot? It is a graph used to display ordered pairs that come from two measures being taken. Can you see this color okay? Sort of. Being taken from each participant. So we have, one sample, but we're taking two pieces of data from each, and it is numerical data, unlike when we were doing the chi-square test for independence. Those were categorical, one sample, two questions. We're looking for independence. Here, one sample, two questions, but it's two numbers that we're taking, so two measures. So it's quantitative data. So I'm going to write this again. Must be numerical measures. Okay, so when do we use a scatter plot? Well, we use it when we want to investigate whether or not any pattern of behavior exists. We want to look at the scatter plot to see if there is a pattern amongst all those data points. I'm going to switch colors to something darker. All right, so how do you make a scatter plot? Well, we will be using our TrustDTI 84s quite frequently. I have to go across the room to get mine. And so what we're going to do is we're going to enter all of our x coordinates, which is our, we call those our explanatory data, or explanatory data into L1, and then we enter all the y coordinates, which is our response variable, into L2. Second, y equals to get that plot number one, just like we were doing before. But now we are going to be doing, when we were doing our histograms before, but now we're going to do the first one, which is our scatter plot. And instead of just having one list, they'll ask for two lists. So you put your two lists where you entered your data, L1, L2 for your explanatory variable and your response variable, and then push zoom 9, just like we did before, to zoom in. So that should be pretty straightforward to you. You have that all there. So you have to turn to the back. So how do we assess a scatter plot? So we're going to have different things we have to look for. Every time we are describing a scatter plot or an association, we're going to talk about the form, the direction, and the strength. So our three main categories is we're going to look and see if there is a linear association, which is what you would expect it to be, looks like a line. If it's not linear, but there is a pattern, we might say it's a curved association. That could look a lot of different ways. It could look exponential, it could look quadratic, it could look something else that's just a pattern, but not straight line, it's curved instead. Or we could say there is no association, which it looks like there is no pattern. Pretty straightforward. The direction is going to either be positive or negative, uphill or downhill. And the strength, we'll say it's strong, meaning all the dots are very close together in that pattern, forming that pattern. Or we could say they're weak, like we can see that it's going uphill, but they're really far apart. Or we could say fairly strong. We could say moderately strong, or weak in either of these cases. So we could sort of, define them like that. Or sometimes I've just seen it saying moderate. There's not any specific ways to say it, and it's a lot of the strength in particular is very much a judgment call. But yeah, so that's kind of a a nuanced thing. All right, so here's some scatter plots. What do you notice? Well, this is a situation where there is no association. If there is no association, we do not say a direction and we do not say a strength because there is no association. They have to have that form before you can start talking about the direction or strength. Okay, so that's no association because they're just like scattered everywhere. This next one, you can see it's going downhill. I would say this is a linear association. Even though my line looks a little bit curved, I would go ahead and say this is linear. You can see the dots are scattered a little bit kind of far away from my line. So I would say it is fairly strong. And it is negative because it's going downhill. Okay. And it is, all of this is a, yes, linear, said that. All right, down this next one, we can see that is a curve. So that is but all of those dots are super close to that curved line that I drew. If I drawn a little bit more carefully, it would even look better. So I'm gonna say it is very strong, negative, curved association. So I didn't put them in the same order, but I said it all in one sentence, and I hit all three things. All right, so this one looks like it's going uphill. I would say it's maybe a little bit stronger than the one above, but yeah. So I'm just going to say a strong, positive, linear association. All right, without a number to define some of these things, that strength, it's really hard to decide whether you're going to call it strong, positive, or strong and not positive, strong, weak, fairly strong, moderately strong. All those things don't really mean much without a number, which we will get to. So, how to describe an association? Well, we just talked about this, but right here is another thing to do here. So it's positive, it's going uphill. So I'm just drawing a sketch, or it's negative, going downhill. Linear is if it goes in a line, curved if it has some sort of curve to it. And a weak association. So if I have a graph that looks like this, a scatter plot that looks like that, that is going uphill. You can see if I drew two lines on the outside, it's just a wide bar there. So I'm going to call this one weak. And if it is a little bit less than that, but still going uphill, those look pretty much the same to me, but I might say moderately weak. And then the closer they get to a straight line or a pattern in general, I would say moderately strong. And then if it's super close knit there, I'm going to say a very strong association. Oops, not strong, strong. Okay. All right. So it's, that's the whole idea. The closer it is to that pattern. And then we also have to, of course, look out for any unusual features such as outliers or a change in direction. So, so here, this is if you have most of the data is down here and you've got this line up, this one point up here, we'll call this an outlier. And this one is just a regular outlier. But if we have an outlier, we'll talk more about this in a later chapter. There's some outliers based on where they are. They're called an influential point because it influences your whole model that you're going to create. So that's called an influential point, and we'll talk more about this in chapter 8. Okay, influential points. Alrighty, so there we go. On the back of this, when we are looking for an association, we sometimes have an idea of how the variables relate. If there's one variable that we think is reacting to changes in the other, we generally put that reactive variable on the vertical axis and call that the response variable. I mentioned that before, that's our Y list, because it's responding to the other variable. And the one on the horizontal axis, or the X variable, is our explanatory variable. It sort of explains what's happening to the others, supposedly. All right, but sometimes it doesn't matter, and we need to simply pick one of them. So if we have height and weight that we're talking about, who is to say, is your weight depend on your height or height depend on your weight, or anything like that, or which one is the explanatory and the response? And I think I have to be really careful, because just going to say this, we're going to talk about it a lot, but we are not talking about causation in any cases, even though we call them the explanatory variable and the response variable. We're not saying that one thing causes the other in any of these problems. So just watch out for that. Okay. So, basically, these associations, they look really similar. They're just like mirror images of each other, basically. And we just need to decide which one we will be making predictions for. And the one we're going to be making the predictions for, that's what we want as our response variable. So now we want to describe these associations of the scatter plots in context. This is going to be some actual writing that you're going to have to do. So the association, that's how we're going to start all of them. The association between the two different variables, and then we're going to say is, and we'll talk about its form, direction, and strength. Okay, so the association between food costs and cost of women clothes. That's what makes it in context, that I'm saying the association between those two variables that I just got pulled right from there. So I'm just going to say the association between those two variables is, well, it's positive. It's going uphill. Linear and strength. I don't know. It's pretty good. It's not strong, but I'd say it's moderately strong. All right, great. Next one, the association between. That's how we're going to start. The association between. This is average hourly wages and hours to earn an iPod. Work hours needed to earn an iPod. I think it's even, what do you mean? It's an iPad. I can't read. They even have iPods anymore. And average hourly wages is, okay, so that's just that beginning part. And now I can see this is curved, but the dots are very close to the curve. So I'm going to say that it's strong, curved, and it's going downhill, so it's negative. So I'm going to say strong, curved, and negative. That's what that says. Sorry. Okay, next one down here. This, it seems pretty weak here. But we start with the association between working hours and clothes index, whatever that is. Is weak, negative, and I don't really see a curve. So I'm going to say and linear. All right, and this last one, I see no pattern. It does not look like it's positive, negative, I don't see a curve, I don't see anything. So this is the only one that's gonna look a little bit different when we write it. I'm gonna say there appears to be no association between vacation days and food costs. All right, so we still have that context in there by talking about the two variables, and that's it. So nice. Now, one word we've been using over and over again is association. Association just says how they are related, that they are related in some way. But now we are talking about something specific, which a lot of people use these words interchangeably, but they're not interchangeable. But this word correlation is actually a statistic. That means it's something that's calculated, right? From a sample. So a statistic calculated from two numerical variables that measures the strength of a linear association. All right, so I'm going to rewrite that. A statistic calculated from two numerical variables that measures the strength of a linear association. It only is used for linear associations. Now remember before when I said, oh, it's hard to say, is it weak, is it moderately weak, is it strong, is it blah, 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 because it's all sort of an opinion I just shone lights on. But now this number, let's see if it, okay. You can see much better with the lights on. All right, so that number is going to help us make those judgment calls, and it means something to everybody. It's not our opinion whether it's strong or moderately strong or fairly. That number is a universal number that means the same thing to everybody. Okay, so before we can use this word correlation, we need to check the following conditions because we can't use correlations for everything. It has to be quantitative variable quantitative variables. Never use the word correlation if you have categorical variables. If either one is categorical, don't do it. They have to be two quantitative variables, okay? So straight enough condition. If you see a curved pattern in the scatter plot, then correlation is not for you. You could get a correlation, that number, but it won't mean anything if you start with a curved pattern in your data. So don't do it. So no outliers condition. If you see an outlier or an influential point, calculate the correlation twice. With and without. And see if there is a big or small difference. Okay. Sometimes an outlier makes very little difference on the correlation, and sometimes it does make a big difference. So we would need to know that information. Okay, so how a correlation is calculated. So I wrote this all out, but basically, just so you know, each x-coordinate and y-coordinate are separately turned into z-scores, and then multiplied those z-scores. And then the products of all of the z-scores from all of those then they're all added up, and then we divide by n minus 1. I forgot the other parentheses there. So you're never going to have to actually calculate by hand. The calculator will do it for you, but that's what's happening here. So Things you do need to know about correlation. Its notation is, just like it says here, it's R, a lowercase r. There is no units. Why? Because it's calculated from those z-scores, and when you standardize, you get rid of those units, remember? So it will not be affected by change in units of any or all of the variables. So because they go to standardized scores, it doesn't matter what your units are. So if you change one of your variables from feet to meters, it's not going to change the correlation. And it will not be affected by switching the explanatory or response variables, like we saw in this, the height and the weight situation. Doesn't matter. Okay. There is a little more, I think, that I ran out of room. It's on the bottom of this next page, the last fun fact, and it's really, really important. It's down on the bottom of this page. Correlation only takes on values between -1 and +1. Okay, it's always going to be then between those two numbers. So this is perfectly linear. A 1 is perfectly linear, just a completely straight line. Perfectly linear. But so is -1, is also perfectly linear. It's just that +1 has a positive slope or a positive trend, and -1 is an association with a negative slope, which means that the 0 right in between is where there is no association. The closer your R is, or your correlation is to 0, the weaker. There's no linear association. That does not mean that there is no association whatsoever. It could be a curved association that cancels each other out and gets close to 0, but there's no linear association at 0. The closer it is to 0, the less linear association there is. The closer it is to the outside edges, the stronger those correlations are. Okay, so up above here is what not to say about correlation. Don't say correlation when you mean association. Don't correlate categorical variables. Make sure the association is linear. Don't assume the relationship is linear just because the correlation coefficient is high. I'm going to write this. Always look at the graph. You can have a high correlation coefficient that actually has a curved association. And so that is something you always have to look at the graph, and always beware of outliers, and be ready to calculate to both ways. And finally, last but not least, correlation does not equal causation. Even if we see a very strong correlation, a perfectly linear correlation, that doesn't mean that the explanatory variable causes the response variable or vice versa. It means there is a correlation that as one increases, the other increases, or as one increases, the other decreases. It tends to. It does not mean that it's causing anything. So be really careful about that. And when you are, I'm going to write a sentence here, actually. Two variables can have a very strong linear association, but neither is the cause. Okay? Or it could be that the wrong one we think is causing the other one. We don't really know. All right, none of the things we're doing here is designed to decide those. You would need an actual experiment, controlled experiment, to find any sort of causation. So just remember that. All right, over here. Here we have a scatter plot. So we look at this association, and this is the number of storks and the human population over a course of 7 years in 1930s. So it's pretty clear that the more storks there are, the higher the population. So this is kind of a joke that, because that whole, where do the storks bring babies? So if there's a lot of storks, they're bringing a lot of babies in the human population. So that would be an assumption of causation. when in reality, it's that storks, it says on here somewhere, storks nest in house chimneys. So the bigger the population of people and how many houses there are, there's more chimneys and more places for storks to nest, and therefore. So actually the human population increase caused the stork population to increase, and so the other way. So you cannot assume correlation from you cannot assume causation from a scatter plot, even if it has a high correlation. And then there's also the whole lurking variable, which we have talked about before, and we'll review it again here. A lurking variable is a variable that is not one of the ones we are currently graphing, that has some effect on either or both the response and explanatory variables. So that is something that if, another reason we cannot claim any sort of causation, it could be two completely different things. There's a whole website. I got to look up what that is. All these different ways to show correlation between different variables, and have nothing to do with each other, and there's no cause. It's always a lurking variable. All right, let's talk about these just checkings on the next page. Your stats teacher, hey, that's me, tells you that the correlation between the scores points out of 50 on exam 1 and exam 2 was 0.75. Before answering any questions about the correlation, what would you like to see and why? So the first thing you should say, well, the first thing I want to see, I'm seeing it, I want to see the graph. I want to see what it looks like, because is it linear? If it's not linear, then the correlation is not useful. So the first thing I want to see for number 1 is a graph of the scatter plot. Number 2, if she adds 10 points to each exam 1 score, how will this change the correlation? So I want you guys to think about that. And hopefully you came up with the answer that it's not going to change the correlation. If everything changes by the same number of spaces, we add 10 to each score, then the correlation itself is going to stay the same. Okay, it's like changing units. Basically, that's sort of what you're doing there, and it does not change the correlation. If she standardizes the scores on each exam, how will this affect the correlation? It also will not affect the correlation, because that's, again, just changing the units or standardizing the scores. Number 4, in general, if someone did poorly on exam 1, are they likely to have done poorly or well on exam 2? Explain. All right, so our correlation is 0.75, which tells us, if we look back over here, that it's somewhere over here, 0.75. It is a positive slope. Our correlation is going uphill. So if I sketch this, it's going to look like this. 0.75 is not the slope. It just tells us how far away from the lines the points are of where that, the line that doesn't actually exist yet, but that's the idea, how close those are to a straight line. And so if somebody does poorly, has a low score on exam 1, if this is exam 1, and this is exam 2, we would expect them to also have a low score on exam 2, because and we're going to see this positive trend. If someone did poorly on exam 1, can you be sure they did poorly on exam 2 as well? Well, I just drew this. That doesn't mean that's what happened. There could be somebody who did very poorly here and still get a high score. We haven't seen the graph. There could be an outlier. That is a possibility. So we cannot be sure. We can never be sure. Yep, that's what I have to say about that. All righty. When your blood pressure is measured, it is reported as 2 values: systolic blood pressure and diastolic blood pressure. Question: how are these variables related to each other? Do they tend to both be high or both low? How strongly associated are they? So here we can see there's a scatter plot. And so you can see this trend. So before we talk about the correlation, which is going to tell us how strongly associated, that's the number we put for that, the strength of the association, we have to check our conditions, quantitative variable conditions. Both of the blood pressures are measured as numbers, so that works straight enough. We look at the graph, it looks linear, all right? outlier condition. There's a few that are kind of farther away, but none of them appear to be like crazy outliers, so we're good to go. So if the two quantitative variables, the correlation can be calculated, and I'll show you how to do that. And there we go, R equals 0.792. That is how strongly measured they are. The scatter plot shows a positive direction with the higher SBP going down, with higher higher DBP. So the higher your diastolic blood pressure is, the higher the systolic blood pressure tends to be, because it's a trend. All right, there we go.